So when we do our decoding, as I mentioned, we are going to exploit correlations, redundancy, which were introduced between our code words. Okay? So the decoder has to exploit the correlation. So we start with this data, which is modeled as being completely independent. One data bit from the next, I don't know what's coming. And I put it through an encoder. The encoder introduces correlation, right? You know, that U1, it depends on what 1, 2, and 3 are in the register. So there's a dependency that is introduced. And the decoder exploits this dependency, this correlation, which becomes the structure in the trellis. And essentially, when we look for a maximum likelihood detection in such a situation, we're actually looking for a maximum likelihood sequence estimation. So as I mentioned earlier about we're going to look for a path describes a sequence. So when we're doing our detection, we are essentially doing what's called maximum likelihood sequence estimation. And there's a very effective algorithm for finding the maximum likelihood sequence estimate, and that is called the Viterbi algorithm, and that's what we'll be describing for our decoder. So let's see how the decoder operates. What are the operations it performs in order to do the decoding? It will determine what are called branch metrics. Branch metrics, this is a branch. I go from B to C, this transition, and that branch is going to have associated with it a certain feeling, let's just call it that, for how likely an error was to have occurred here or not. These are called branch metrics. So everywhere in our trellis, we're going to be assigning values to all of these transitions. And these transitions are going to be based on what it is we actually received. So this is the encoder structure. This encoder structure is based on, you know, these code words and this code, this collection of coded outputs determine which encoder I was using, and therefore this encoder corresponds to the one we saw in the example previously. And the previous example, I put through this sequence of data through this trellis. We saw that go on. What I want to point out now is that when we use our decoder, we're also going to use a trellis. For sure we're using a trellis. So we're going to take the same structure and we're going to repeat it, only this time the decoding is going to be based on what the received vector is. So Z is the received vector. I should write this over here. M is the transmitted message. U is the coded transmission, and Z is the noise corrupted received signal. So the encoder takes M. The encoder takes M and gives you U, and then U is transmitted. That's the job of the transcoder. Now in the decoder, I start out with Z, which is the noisy contributions. And here is going to be what is received at the receiver, and we will introduce some bit that was flipped as it went through the transmission process. And so now we're going to discuss how can a decoder come up with the best sequence, the most likelihood sequence of bits that was transmitted. And we'll see that in order to do that, we're going to create these branch metrics, which are going to be written next to these valid transitions. So in the encoder, the valid transitions contain code words. And in the decoder, the valid transitions will now have a branch metric that we'll be calculating. So how do we calculate what that branch metric is? Well, I need the encoder in order to build the decoder. So let's say that what I receive in some time interval, and remember one of these tiles here is a time interval. Suppose I receive a 1-1, and I'm assuming that I start at state A, because I know that all transmissions start from state A. I look up at my decoder, my encoder, and I say, well, the transition from A to A should put out a code word of 0, 0. What I received was 1, 1. So that means that if the transmitter really sent 0, 0, and the receiver got a 1, 1, that meant that there were 2-bit errors. Both of those bits got flipped. So the branch metric that I'm calculating is the Hamming distance. How far is 0, 0 from 1, 1? Hamming distance is the number of bits that are different. There's 2 bits that are different. So next to this transition A to A, I write 2. Because if there really was a transmission that led to a transition from A to A, that meant that there were 2 errors during that transmission. Now I look at the other possibility. When I go to A, from A, I could have gone to B, and I look in B and I say, well, the distance between what was received and the code that would have happened on this transition is 0. Okay, so then there would be like 0. And then you can ask, is it more probable to get no bit errors or to get 2-bit errors? Okay, so you know that the probability of bit error certainly better be less than a half. If I'm in a channel where more than half the bits are getting flipped, that I should not be transmitting signal, or, well, whatever. You can always count on the system having a probability of error that's less than a half. So that means that the probability of no errors is a lot more probable than the probability of 2-bit errors, or 1-bit error, but certainly 2-bit errors, like big difference. Okay, but we're not going to do that, all right? That would be like making no sequence, just picking which one is it. So we're not going to do just that, but we're going to keep going. So we have a lot more of our trellis to exploit. But the important thing I want you to get from this exercise is just how do I build my decoder trellis? So this is the way we build a decoder trellis. We take, during a time interval, what was the received sequence? So this is our hard decisions we got from our demodulator. And for each one of the transitions that are available in that time slot, now I've got 4 transitions in this time slot. Because I know I started at A, but now I could be at A or B. So I have 4 branch metrics that I have to calculate. So I take the difference, 0, 1, and now I have 4 values here in the encoder, and I step through each one of them, and I calculate what is the Hamming distance between what was truly received and what might have been transmitted. And so now I have 1, 1, 2, 0 as the transition possibilities, the branch metric in that transition. Of course, I get to the next one, and now I'm in sort of steady state. Now there are a total of 8 transitions which are possible. And as I go forward, there will always be these 8 transitions which are possible. So in this case, I have 0, 1 as the received code word. And I look at the valid code words, these 8 valid code words, and I calculate the distance between the code word received, corrupted, noise-corrupted code word, and I calculate the distance, the Hamming distance between each of them. So, having filled up my decoder, this is just like step 1. Just go through and fill it up with all of this. This is my output from my demodulator. What does my trellis look like, my decoder trellis? How am I going to use this decoder trellis to actually decode the signal? Now, to understand that, we have to move from branch metrics to path metrics. So here we had branch metrics. So I need to find now, instead of a branch metric, now I'm looking for something called a path metric. A path metric is going to be a function of all of the branch metrics along a path. So let's look at just 2 paths possible that I trace through my trellis. These are valid transitions because they follow the lines that I've established before. And I have, going to a certain point at the 5th time interval, if I'm at state A. Suppose I'm at state A, there are 2 possibilities of how I got to state A at time 5 that I happen to draw here. In this case, there's 2. And each one of these paths has a different history behind it. So the transition that's dotted is a 1. Transition that's solid is a 0. So if I look at the upper path, that would be a 1, a 0, 0, 0. If I look at the bottom path, that would be if I had transmitted a 1, a 0, 0. Okay, so 2 potential solutions. solutions of what was transmitted, a sequence of what could have been transmitted, is represented by a path in the trellis. And each one of these paths has a path metric assigned to it. And the path metric is just the sum of the branch metrics. So in this case, I said it was 1, 0, 0. And I've taken my decoder and I look at, along those transitions, what were each one of the branch metrics, and I add them up. So I get, there was a 0, there was 2, 1, 1. That gives me a branch metric of 4 for this path. Okay, so I have a path metric for the 4. Now I do the same calculation for this other path. And again, this path corresponds to a 1, 1, 0, 0. That would have been my choice. And on this path, I add up all of the branch metrics, and the path metric I get is a 1. So if I followed the path up here, I call this the upper path and the lower path. This one comes in from the upside. If I do that, I would have gotten a path metric of 4, and if I do the other path, I would have a path metric of 1. So what does that mean in terms of Hamming distance? I could have had 4-bit errors, or I could have had 1-bit error. And I ask myself, which is more probable? Which is more likely? Is it more likely that I had 4 errors, or is it more likely I had 1 error? Well, 1 is smaller than 4, and in a channel p less than 0, that would be more likely. So the bottom path is the more likely path of the two paths. So there's only 2 ways I can get to state A. I could have come from state B, or I could have C, or I could have come from state A. That's the only way to get to state A, coming from A or coming from C. And in these 2 examples, where there's 2 possibilities are traced back with 2 different lengths, what I do is I pick one of them to survive. Although there are always 2 possible paths to go to any one point, I don't allow myself to keep 2 paths. I force myself to pick one which is better than the other. And the way I pick it is based on the path metric. And I call the one that I keep the surviving path. So in this case, the lower path is going to be the surviving path. And the other path I'm going to eliminate. And so this idea of choosing path is how the Viterbi algorithm is able to be a computationally and memory efficient way of finding the most likely path through a trellis. And the best way to see how this algorithm works is to actually step through it.